All right, how's it going, everybody? We are here on Thursday, February 11th. We're going to be talking about section 7.2 today. This week in general, we're going to be hitting all of our trigonometry ideas with calculus here. Today, we're going to look at a bunch of integrals that have trig functions in them, and we're going to see the types of substitutions we're going to want to do and trig identities we're going to want to use to handle those things. In our next video in section 7.3, we're going to look at a bunch of integrals that don't have any trig stuff in them, and we're going to make some trig substitutions, right? So in our section 7.3, that's when we're going to recognize that some of our substitutions that it's going to be useful to us to put trig functions into integrands that currently don't have any to take advantage of some trig identities to simplify those expressions there. So today is integrals with trig and dealing with it. Tomorrow is integrals without trig, and we're going to put the trig into it to take advantage of some trig identities. Based on the fact that we know that we're going to need a bunch of trig identities, one of the things that we all want to remember is I hope you remember that you looked through all your identities when you took your trig class. I'm guessing that some of you still have a trig textbook, and I'm guessing that some of you don't. So one of the important things that you have access to in Canvas is I did post this. This is just a scan of the insert. I just called this thing the trig book insert. This is posted, by the way, in Canvas. If we go to our class here in Canvas, then you can see this is going to be sitting here in our week 5 module, the trig book insert right here. So this PDF right here of all your trig identities is definitely something that you're going to want. I definitely don't expect that everybody just straight up remembers all of these or even most of these. I absolutely do expect that you could look at basically the ones that are on screen right now, right? Basically all these guys right here. All these are available to us to help rearrange a bunch of our trig expressions. And so again, it's not like you remember exactly all of these, but I expect you to be able to say things like, I have a cosine of 2x. What do I think I can do with that? And to scan around here and to say, oh, here's some expressions for cosine of 2x that I could maybe do to rewrite some things out there. Stuff like that, right? So just kind of recognize that you're going to need this because there's no way that I don't remember these. Therefore, there's kind of no way that any of you guys remember all of these out here in order to take advantage of them. So grab this PDF from Canvas, especially if you don't have your trig textbook, and this will be valuable to you for the course of this week here for both this section and the next section here. So one of the things I think is good to kind of recognize here is that I think a pretty typical thing to do when we're all taking our trigonometry class semesters ago is to say, a lot of times when we're dealing with our trig identities, when we verify identities, and when we solve trig equations, one of my go-to things is always to say, out of the 6 trig functions that there are, there's really 2, right? We basically need sine and cosine. Those are kind of the essential 2 out of the 6. And so a lot of what I do when I teach trigonometry is every time and I'm getting ready to start the chapter 7 in trig this week here, is to say I want to convert everything in terms of sine and cosine so that I'm in my sort of base functions, and then I proceed with the problem. What we're going to find here is that's not necessarily going to be in our best interest all the time. Sometimes it will. We will do a little bit of that here today, but that's not going to be as common of a strategy associated with integration as it was in just dealing with the identities and solving trig equations before we had calculus, right? Instead, a good thing to recognize is that the 2 major techniques that we have so far, U substitution and integration by parts, both of them require us to do this job of identifying a component and identifying the derivative of that component. And so that's going to be one of the reasons why it's not necessarily helpful to always convert to sine and cosine, because we're going to see things like, the derivative of tangent being secant squared, stuff like that. I want to kind of, if I see tangents and secants, then I kind of want to leave those parts in there because one is the derivative of another. So that might be helpful for my substitutions. But one of the things I'm kind of thinking right now is how many of you even remember that the derivative of tangent is secant squared? Well, maybe we should go ahead and talk about our derivatives of our 6 trig functions right now, since I'm assuming that some of us have forgotten some of these things here. So let's go ahead and real quickly remind ourselves of what are the derivatives of our 6 essential trig functions here. Because if you don't know these, then you're going to be in an awfully tight spot to actually come up with any of the substitutions that we're going to need to perform here. So let's remind ourselves of these, and also kind of remind ourselves that, like, let's see, resize this a little bit here. that you can come up with these on your own. I think the important thing here is that as long as you can remember the derivatives of sine and cosine, you can come up with the other four on your own. So we all remember that the derivative of sine is cosine, and that the derivative of cosine is negative sine. In general, we're kind of seeing just between these two statements right here, it seems like derivatives of sine and of cosine repeat every four derivatives. You go sine to cosine, cosine to negative sine to negative cosine loops back around to sine again. So four derivatives, we're always going to repeat the functions that we've seen there. Now, when we look at derivatives of tangent, we want to remember that this is just the same thing as doing the derivative of sine over cosine. This is like one of the very few times in my life I'll ever actually stick with using the quotient rule. So I'm going to do low d high minus high d low all over low squared. It looks like I'm getting cosine squared plus, I wrote that one wrong right there. I was like, that's not right. Let me fix this guy right here. It should have been low cosine d high. Derivative of sine is cosine minus high is sine. D low, derivative of cosine is negative sine. I had that one wrong right there. So it looks like we're getting cosine squared plus sine squared. We know, here's our first use of a trig identity today. I think it's the one that most of us, or that is the most commonly remembered. Sine squared plus cosine squared is 1, and that's what gives us our 1 over cosine squared of x, and that is exactly our secant squared. So the derivative of tangent is secant squared there. Very similarly for cotangent, we're recognizing that this is going to be the same thing as the derivative of cosine over sine. So let's do the exact same thing here. That's going to give me low d high. Oops. Again, I'm just saying derivative and then writing down the exact same thing instead of taking its derivative here. Derivative of cosine is negative sine. Low d high minus high d low all over low squared here. That's going to be sine squared of x. And it looks like here I'm getting negative sine squared minus cosine squared. So it looks like that's actually going to be a negative 1 on top. I had negative sine squared and negative cosine squared. If you factor out the negative, that's just negative times sine squared plus cosine squared, which is 1. So I'm getting a negative 1 in the numerator over sine squared on the bottom. And that's giving us negative cosecant squared. For our derivative of cotangent, we can continue playing some quotient rule games here for secant and for cosecant. Give myself a smidge more room right here. Come on, mouse, you can just click it instead of highlight things. That's okay. That's okay. All right, our derivative of secant is, we always want to remember, we can rewrite this in terms of our sines and cosines. That, man, write things all over the place. What's that equal sign doing there? Draw. Let's see here. 1 over cosine of x. I'm going to do my low d high minus high d low over low squared. Low d high minus high d low all over low squared. It looks like we're getting 0 from the first term. We're getting a positive sine x on the second term. So that's going to give me sine x over cosine squared x. Typically, we break this off to say sine over cosine is tangent. 1 over cosine is going to be our secant there. So this is going to be tangent times secant. And very similarly, for our last one here, cosecant, take the derivative of 1 over sine of x. And we're going to see here, we're going to get a low d high minus high d low all over low squared. And again, I'm seeing 0. We're getting a negative cosine on top. We're getting a sine squared on bottom. So I'm seeing here we're going to get a negative of cosine over sine is cotangent. There's still one sine remaining on bottom, so a 1 over sine is going to be our cosecant. All right, so we've got our derivative there of cosecant. It's negative cotangent cosecant. So we've got our six derivatives of our trig functions. You got to know these ones because we got to know what partners to look for out there, right? We know that when we're doing both u sub and Austin. So to find these derivatives, I'm just using the quotient rule. That was four applications of the quotient rule is all I did right there. We haven't done any substitutions here yet. Just using the quotient rule so far. The reason that we care about all these is because both u sub and integration by parts require us to recognize both a component and its derivative. So I want to have in my mind things associated like tangent and secant squared. If I had the integral of tangent of x times secant squared of x, that's going to be a super easy integral because I can just let u be tangent and du is going to be secant squared of x dx, and I've just got the integral of u at that point, right? So recognizing functions and the derivatives as partners is going to be helpful for all the substitutions that we want to make here. So let's go ahead and look at our first integral here of a trig expression. And we're going to do the easiest one to get started because that's where we should always start. We're going to do the easiest non-obvious trig integral right here. And there is at least one small lesson that we should be taking away from this one, even though we've already done this one here. We've seen this one before. I'm going to think of this. This is going to be one of the few cases where I do want to rewrite this guy in terms of sine and cosine here. And when I do this, what I'm kind of recognizing for myself is I do see sine, I do see cosine. I know that sine's derivative is cosine and cosine's derivative is negative sine. That negative is just a constant multiple, so that seems just fine. I can deal with that part right there. It seems to me like it's possible that there's two different u subs that we could do right here. So I'm thinking to myself, well, let's just go ahead and pick what seems like the most natural choice to me right here. And if I do my u being sine of x, then I'm going to get du being cosine of x dx. And now I'm stopping and I'm thinking to myself, all right, I want to do u is going to be sine, but notice here, I don't actually have a cosine of x dx. This cosine of x is in the denominator. This dx is officially multiplying the fraction. This is part of the numerator up here. I have a dx divided by cosine x. I don't really have a good direct way to actually make this du substitution here. It looks like this one's not going to work out because this is cosine of x times dx. Over here, I have dx divided by cosine of x. I actually don't have the right terms right here. It feels to me like either of these u subs should work out, but it looks like this version is not going to right here. I need to make sure that my du term has only the components that are up in the numerator of the fraction right here. So that's leading me to believe maybe we should do a different u sub here. Pick cosine of x, let my du be negative sine x dx. And if this is what I'm doing here, I can do both these parts. Cosine of x is going to be the denominator, that'll be u. Sine x dx I do have up here as a numerator term, just like my du term should be. So it seems like in this case here, this is we have to pick our substitution to be this direction right here. And so I just wanted to do this one just to kind of point out, like, don't forget the same lesson as we talked about in 7.1. When you're doing u sub, when you're doing integration by parts, it matters that you have a little bit of persistence here. It's okay to try some things, recognize that they don't work out, try your other choices. There's not exactly a ton of options that are out here for us. So it looks like I'm going to be rewriting this. I am going to take on a negative here. I'm kind of moving that negative to the other side to be with du. And it looks like we're getting 1 over u du, right? Again, cosine of x became u. Sine x dx is what became du, including a negative right there. And this is going to lead me to negative natural log of u. And then we just got to make our substitution for u going back in here. So negative natural log of, it looks like for our appropriate substitution here, this was cosine of x plus c here. And I do think a more typical thing here is to recognize that that -1, anytime we have a multiple, constant multiple of a natural log, we can treat this as a power on the inside right here. So this is like cosine of x to the -1 power, also known as a 1 over cosine of x. So it's typical for this to be rewritten as secant on the inside right there, because that's absorbing the negative that was sitting on the outside right there. So I wouldn't be upset if I asked you to integrate tangent and you gave me the first version right here. But in general, I think you should expect to see, like the book would tell you, stuff like this. They're using that negative as a -1 power on cosine. It says take the reciprocal. Reciprocal of cosine is secant. So there we go. There's our first one, and our first tiny lesson right here, which is we're going to make some substitutions that might not work out today. It's okay to just put things down on paper, try them, recognize that they won't work, try something else. There's a pretty limited number of possible substitutions we could make, at least in this case right here. We're going to see our options are going to spread out a little bit here coming up. So let's take a look at our next example, something a little bit more exciting. Our next three examples that we're going to see are going to be things dealing with products of powers of sine and cosine. I really should just say powers of sine and or cosine. We'll see a couple of the ones that we're going to do right now are only going to include one of our two trig functions rather than products of both right here. But I think this is a good first example for us to see as far as what types of substitutions that we want to make because I'm hoping that the thing that you're kind of recognizing here is that we've got both sines and cosines, and that leads me to believe that there should be a relatively direct u substitution that we can do. The other thing that I see that's really nice for me here is that with tangent, we had this issue of there being a ratio, so we had to pick the proper choice of u being sine versus being cosine. To make sure that our du term ended up being associated with terms that were in fact a product rather than terms like 1 over cosine times dx that were more like a ratio, right? Here, because there was a fraction, it mattered what we chose for u and du. Down here, it doesn't seem like we have as big of a concern about that. What we are going to end up coming to find, though, is that the even and odd powers are going to be some things that are going to help us make the decisions that we want to make right here. But I'm thinking to myself, I'm just going to go ahead and do what I've been encouraging you guys to do, which is essentially like, it's okay to just kind of make a guess right here. We are going to form some more general strategy right now, but like we're exploring right now. I think that the most natural guess for me to make right now, the thing that I think would be easiest to me, is just doing a little bit of a u sub with u being sine of x. And let's see where that takes us here. If I choose u to be sine of x, I think this is a good choice because du is going to be cosine of x dx, right? And this is one of those places where it's not clear to me if this is going to be a great substitution yet. And the reason it's not clear to me is because it looks like we can rewrite this as u to the sixth for sine to the sixth of x. But my problem here is that this is a whole cosine cubed dx, right? Only one of these three cosine terms is going to be what I have associated with my du, but there's still two powers of cosine remaining. So I'm going to write this as cosine squared of x times cosine x dx. Right? I've split up the cosine cubed into my two parts right there. This is going to be my du, but I still have a cosine to the sixth remaining. So now I'm looking at this asking myself, all right, maybe I didn't make the right choice for a substitution. Maybe we should be parts in this. What do we got going on right here? Well, cosine squared, does that look like anything special that you should recognize? Yes, I think that this is one of these places where we should recognize that we've got a trig identity available to us here. Our Pythagorean identity, I think, is one of our most generally useful things to remember here. It looks to me, very conveniently, that I can rewrite cosine squared as 1 minus sine squared. The reason that's really practical to me in this case is because I have u being sine. This is going to allow me to write cosine squared of x in terms of u, despite the fact that u is a sine expression. Cosine squared, obviously, a cosine expression right here. So I'm kind of using my trig identities to force the remaining pieces of my integrand all to be in terms of that one thing, sine of x, because that's what I defined my u to be here. So in this case, it looks like we can do a little u to the sixth. That's going to be a 1 minus sine squared of x. That's our new cosine expression there, du. Again, I'm still not in good shape with my integral. I got some u parts, I got some x parts. I need to be all in terms of one variable, u, because that's our variable of integration right here. But now it looks like I can get there. U to the sixth times 1 minus u squared du. And now I'm pretty happy about this. Now I have converted this trig integral with powers of sine and cosine into just a polynomial integral right now. So this should be pretty easy for us to knock out now. Looks like we got a u to the sixth minus u to the eighth du. Which is going to give me 1/7 u to the seventh minus 1/9 u to the ninth. And all we got to do is plop back in our sine, and we are all good to go here. So this is kind of our first example of using our trig identities to make some replacements in here, right? I think the Pythagorean identity, again, as I kind of said, I definitely don't expect that you guys remember like all of your substitutions that are associated with that, the back of the trig textbook there, the trig insert. There's like 40 or 50 identities out there. I don't think you remember all of them. This is like the one where if you were to remember one identity from that entire backside of that trig book right there, the Pythagorean identity is it. Real quick, let's remind ourselves, by the way, that there are actually three different versions of the Pythagorean identity. And that we might want to take advantage of all three of those. So real quick, I'm going to flip over here. Remember that sine squared plus cosine squared equals 1 is only one of the three versions of the Pythagorean identity. We also have equivalent identities that are associated with tangent, secant, cotangent, cosecant right here. So these three collectively are the Pythagorean identities, all three of these. They're all equivalent to each other. The way that we build these, by the way, is you just take that sine squared plus cosine squared equals 1. If you divide this entire equation by sine squared, then you're going to get a cosine squared over sine squared is going to give you the cotangent squared plus 1 version. That's if you divided the whole thing by sine squared. If instead you took our first one here and divided the whole thing by cosine squared, you would end up with the one that's on the second line right here. So those three are all equivalent to each other, and they're all possibly ones that we're going to want to use to manipulate our expressions again, converting one squared trig term into a different squared trig term that we might actually want in that setting. So maybe our like brief little lesson that we learned right here is we kind of really like even powers of trig expressions because even powers of trig expressions are things that we can replace with its sort of partnered expression, right? Cosine squared, we can always rewrite as sine squared and vice versa. So I'm noticing here that kind of what our strategy was is we picked off one of the powers from the odd powered trig function so that it could partner up with the du. We used the remaining even powers to be re-expressed in terms of the other trig function, which put all of the remaining parts of our integrand that didn't deal with du in terms of one trig function, just sine. And that allowed us to get it all in terms of just u, like we wanted, so that we could do the integration right there. This is a pretty general strategy that we're going to use across all of our trig integrals, is kind of identifying when do we have even powers, when do we have odd powers. Even powers indicate that we can do a Pythagorean identity swap. Odd powers indicate that we might want to rip off a single one of those so that it can partner up with the dx, be part of a substitution term right there. Pretty broad strategy that we'll use here today. So now let's look at one where we kind of lose that ability a little bit right here. In our next integral that we want to look at, a definite integral from 0 to pi of cosine to the sixth of x. Obviously, the reason why this one's different than the previous is because in the previous we had both sines and cosines, and so it was sort of slapping me in the face that I wanted to do u sub. All I'm doing is sitting here staring at a function and its derivative, sine and cosine. We had to deal with the powers, but the sine and cosine were just yelling at me to do a u substitution right there. I don't have that kind of action right here. All I'm seeing is the cosine to the sixth of x, right? But the lesson that I learned in the previous one is, well, at least this is an even power on a cosine right here. This sort of leads me to believe that there's some way that we can rewrite this using these even powers of x. Right? I know that I don't really have any identities that are associated with like a cosine cubed or anything like that, right? I'm going to kind of just think to myself, well, I know this is the integral from 0 to pi of maybe another way to think of this is like cosine of x to the sixth. And when I'm looking at it this way, I'm saying to myself, I don't know, like, is that helpful? Like, I don't really have a direct way to rewrite cosine as anything. I obviously don't have a direct antiderivative here. What is it that we really want to do with this guy? Again, think to yourself that we like seeing sine being squared and cosine being squared. We have so many identities that are associated with that. And I'm thinking to myself, if I were to force myself to see this as cosine being squared in some way, I could do that. All right. Now, I don't really know where I'm going yet here with this, but at least I know that I mean, again, if you look on your trig identity sheet, most of the identities are associated either with converting converting between two trig functions or dealing with squared versions of trig functions. So let's pop over to our identity sheet here and see what we can see. So my deal here is I have some version of cosine squared, and I some version of it, right? I have some power of cosine. I don't know what to do. So I'm just scanning all the way around. Let's see here. first thing I'm going to flip over here. So I'm just scanning around, right, for some cosine squared. So I see one in the Pythagorean identity. I see that I could rewrite this as like a 1 minus sine square, but I don't really feel like I'm gaining any ground there. That's just replacing one squared trig function with another. I don't have anything even odd identities going on. We don't have any sums or differences of trig functions going on. That doesn't seem useful. Half angle formulas over here. I don't know. It doesn't necessarily feel like I've got much of these. I don't see any squared things, although I do see some square roots. Um, Maybe, there's some square roots certainly associated with squares there. That might be something we want to think about. Double angle formulas. All right, I'm seeing some cosine squareds out here, right? I'm seeing in this first one right here, I do see a cosine squared there. It looks like it's going to introduce some sine squareds, which I don't quite know that that's something I want to bring in. And it looks like it would introduce some cosine of 2 theta. Uh, eh, eh. I'm seeing a second version right here, though. This maybe looks good to me. The reason why I think that this guy kind of looks good right here, cosine of 2 theta equals 2 cosine squared theta minus 1, seems reasonable to me is because it seems like I've got some cosine squared term, and it seems like what I'll be able to replace it with is basically just an expression involving cosine of 2 theta. I do know how to integrate cosine of 2 theta, give or take some addition, subtraction, multiplication, division of constants out there. So this maybe seems like a reasonable identity for me to use. And again, I obviously kind of know where I'm going with this integral right here, whereas when you're doing these problems, you won't. But I'm trying to emphasize to you that like a bunch of this is just going to be you being like, okay, I guess let's go check the formula sheet, see if I can see something that seems reasonable to me. Anything that seems like not great to me, I'll skip. I'm trying to like come up with my collection of possible ideas. Cosine squared shows up on this sheet like 4 to 3 times, plus some square roots involving some cosine terms. But notice, by the way, this half angle formula is just a rewritten version of the double angle formula that's over here. So whatever. So the point I'm saying here is I saw 3 versions of cosine squared. Those are kind of my 3 possibilities of maybe swaps that I want to make. This one that I have highlighted seems to me to be the most reasonable one because it's going to convert a cosine squared term that I can't integrate into a cosine of 2 theta term, which I think I can integrate right there. So I think I'm going to grab this identity for myself right here, and let's see if we can make something happen with it. So cosine of 2 theta equals 2 cosine squared theta minus 1. Oop, forgetting to flip over. Here we are. Cosine of 2 theta equals 2 cosine squared of theta minus 1, right? Let me make sure I got my identity right. 2 cosine squared theta minus 1. Sometimes I forget if that's a plus or a minus. And again, I don't care. And I don't care if you can remember it either. I care if you can use it, right? This is like reference material that you need to be good at using. This isn't like go memorize all your identities again. I know that I want to see what a swap would look like associated with cosine squared, so let's solve for that. So it seems to me like an appropriate substitution I could make would be that cosine squared is equal to a cosine to the first power. Now we do have that 2 theta on the inside, so that would technically be a little bit of a u sub right there to handle that, a little bit of a chain rule, but that should be easy right there versus I don't even know what I would do otherwise with my cosine squared term here. So it looks like what we're getting here is a integral from, what are you doing to me here, Microsoft Word? Relax. Integral from 0 to pi of. Now, I've still got this cube here, and that's going to be a little bit of a bummer for us, but not the end of the world. So that's the stuff that's being cubed when I make my swap right here. Right? Cosine squared just got replaced with the cosine squared expression there. Right? Still cubed. So here's some things that I'm seeing. One, it looks like I do have a binomial cubed, which is ever so slightly unfortunate for us here. I also have 1/2 cubed as a constant multiplier out front. I don't think I want this 1/2. I don't want these fractions kind of messing around with my other terms inside the integrand. So I'm going to distribute this cubing onto the inside here. So I'm going to get 1/2 cubed is 1/8. Oops. I'm saying 1/2 right there, but I really want to make that 1/8. And I'm also seeing here, it seems like, unfortunately, what I'm going to want to do is expand my binomial here cubed. And that's kind of a bummer because we're going to end up with a whole bunch of terms. But again, this is all going to be terms that are based on this cosine of 2x right here. And that seems like something that's ever so slightly more manageable for me for the parts that we want to be able to handle right here. So let's go ahead and see if we can identify how we're going to make this guy happen here. So I'm going to do two things, right? Which is one is cubing the 1/2 to get 1/8 and pulling it outside the integral. The other thing that I want to do is I want to cube this binomial term right here. I'm kind of thinking about what these coefficients might be. If you recall your Pascal's triangle for the binomial theorem. These should be the coefficients on a binomial cubed, right? This is our like coefficients on x plus y to the 0, on x plus y to the 1, on x plus y squared, we get those guys, and on x plus y cubed, we get these coefficients of 1, 3, 3, 1. So that tells me what coefficients I want to put on the cosine of 2x and the 1 when I go ahead and expand this guy. So that says to me my first term should be one copy of cosine 2x cubed. So I'm going to get a cosine cubed of 2x. My second term should be three copies of cosine squared of 2x times one copy of 1. That's my term right there. My third term is going to be three copies of 1 power of cosine of 2x times 1 squared. And my fourth term is going to be one copy of 1 cubed. Right? And again, I know that I just did a bunch of multiplications by 1 that are trivial right there, but I'm trying to exactly like imitate this the binomial theorem's coefficients that we know of right there. Right? So now I got to say, like, did this actually help me or did this not actually help me? Well, I guess the good news is that each of these there's like four different integrals now that I can kind of break this out as. It seems like some of these are going to be easier, right? I can do the integral of the fourth term. I can do the integral of the third term. That's just a basic u sub. Here we've got the integral of cosine squared. Let's see, how are we going to integrate cosine squared? Oh, well, actually, we can just reuse our old identity again. And then we got to figure out what we're actually going to do with the cosine cube. This one seems to me to be maybe the funkiest one that we've got left right there that we're going to have to actually deal with. Maybe. Let's go ahead and see what we get when we rip this guy apart into four different integrals here. First integral, 1/8. Okay, here's what I'm going to do. I'm going to do 1/8 and put a giant bracketed expression right here. I know at the very, very end, I'm going to multiply all these integral expressions by 1/8. I'm kind of trying to just ignore that till later. So I'm seeing the integral from 0 to pi of cosine cubed of x. Oops, I better not make a mistake here with my singular x. All of these are 2x as the argument inside of the cosine function here. All right, so I've ripped this apart into four different integrals so that I can think about each of these parts separately. Again, what I'm seeing is that some of these seem easy and some of these seem hard. So I'm going to get a little, I'm going to kind of break these off into some parts right here. So I am seeing for our final one over here, integral of 1. I'm going to do the easiest to hardest, right? Integral of 1. Well, that's just going to be x evaluated from x equals pi to x equals 0. I'm going to put my final bracket closure right there. I'm just doing the easiest to hardest right here. When I evaluate this, it looks like I'm getting pi minus 0 for just pi. That's my contribution from the fourth term. Again, there's my closing bracket right there. So there we go. We've done 1/4 of the integral that we need to do here. This one, not going to be that bad right here. Cosine of 2x, we've just got to do a little bit of, in fact, let me give myself even more room so I don't mash myself with the ones that are actually going to take a little bit of effort right here. So cosine of 2x, when I take the integral of cosine, I know that I'm going to get sine But I know if I were to take the derivative of sine of 2x, I would really get 2 times the cosine of 2x. So I need to introduce this 1/2 factor as well. That's my u sub that I'm sort of skipping over right there. And I'm evaluating this guy from x equals 0 to x equals pi. And the thing that I'm noticing here is that I'm really going to be getting 3/2 times, well, when I plug in pi here, sine of 2 pi is 0. Sine of 0 is 0. Ooh, it looks like we actually got 0 for the contribution from this component right here, right? Because sine of 2x is 0 at both 0 radians and at 2 pi radians, which is the same thing as 0 radians again right there. Why did that happen? Why did I get 0? How could I have kind of known that I was going to get 0 from that guy? The way that I can tell is because cosine is an odd function, and this function is symmetric over x equals pi halves. We learned about a symmetry rule earlier this semester that said if you have an integral from negative a to a of an odd function, then that integral will be equal to 0. I'm noticing here we don't have a negative a to a situation, but I am recognizing that cosine is odd relative to x equals pi halves being the line of symmetry rather than x equals 0 being the line of symmetry. Let's go take a real quick look in Desmos to see what I actually really mean by this right here. When I go look at cosine of 2x over here, I want cosine of 2x, and very importantly, I need to be seeing this, the x-axis, in terms of like pi halves as my chunks that I'm seeing here. Let's get rid of these minor grid lines. And when we go look at this guy, what I'm seeing here, and really what I am interested in, right, we're doing the that's like our chunk of interest right here. And what I'm seeing is that the 2 half lobes that are above are exactly equal in area to the 1 full lobe that's below. So I can see that because this is symmetric over this x equals pi halves line, that's how I kind of should have known that I was going to be getting 0 out for that integrand. Let's remember that for a second here. Let's go back to our other integrals here. So we've done 2 of our 4 integrals we need to be able to do for this guy. Let's go on to the next hardest one right here. This one right here, when I say next hardest, I'm seeing it looks like it's going to take some work, but I think I know what I want to do. Cosine squared of 2x, well, it looks like I can just use my substitution again. And I'm thinking to myself, I'm thinking like, ooh, are we going to get that same kind of symmetry as we just got on the previous one right here? Well, I don't know. At this point, I'm thinking, let's just go check it out. Cosine squared of 2x. Am I going to get the same type of action here? It doesn't look like it. And I should have known that because when we get even powers, we're only getting positive contributions. There's no negatives to sort of cancel out the positives to give us 0 right here. So it does look like however much area we're getting, it's certainly not going to be 0. So it looks like I actually have to figure this one out here. But it's worth a look, right? So let's go back and actually do the guy here. So I'm going to go ahead and use my substitution that's up here again in blue to rewrite this guy. So it looks like now, and notice a really important thing here. In this substitution before, we had cosine squared of a single x in the argument. Now we have cosine squared of 2x. So in my identity up here, theta is actually 2x, not theta being 1x like we had before. So if theta is 2x in this case, then I'm actually going to get a cosine of 4x as my interior component here. So I'm going to rewrite this guy as 3 times the integral from 0 to pi of cosine squared of, and maybe here's what I should write, right? I'm going to write that in here. So theta equals 2x in this case right there, not 1x. That's kind of an important distinction that we're making here. So now it seems like I'm going to be getting 1/2. So cosine squared, I'm going to get 1/2 cosine of 4x because we're doubling whatever that argument was inside of the squared. Cosine squared of something, you're going to get cosine of 2 times something. Cosine squared of 2x, we're going to double 2x, which is 4x plus 1 dx. And now this looks like an integral that I can actually handle. So I'm going to get 3/2 times the integral from 0 to pi of cosine of 4x plus 1 dx. I can do this integral now. 3/2 times, what are we going to get here? The integral of cosine is sine, but I know if I were to take the derivative of sine of 4x, I would get 4 cosine 4x, so I need to introduce a 1/4 to counteract the chain rule right there, plus x, right? Integral of 1 is x, and we're evaluating this guy from x equals 0 to x equals pi. And so I'm seeing, what are we going to get here? 3/8 times, when I plug in pi, sine of 4 pi is 0, plus pi minus, when I plug in 0 into sine, oh, wait a second right here. I need to be ever so slightly more careful with this. Well, no, I do. So notice the mistake I made right here. I was sort of thinking that this 1/4 was multiplying the whole thing, so I sort of factored it out to be with the 3/2 right there. I don't think that's actually appropriate because the 1/4 is not multiplying the x right there. So let me go ahead and fix that a little bit right here. So we're going to get 3/2 times, we're going to get a 1/4 times 0 minus pi as my first grouping, minus, now I'm plugging in x equals 0. That's going to give me again a 1/4 times 0 minus 0. And it looks like that's going to be giving me, overall, the only thing I see here is we've got 0 minus pi minus 0. So it looks like this is going to be negative 3 pi halves is my overall contribution here. All right, just carrying those guys down. And I want to keep my bracket on here because the bracket's helping remind me that I'm going to need to multiply this whole thing by 1/8 at the very, very end right there. So did I get that? Oh, I see. Okay, I think I made, okay, my one tiny mistake right here. Also, I'm seeing this is a sum of sine of 4x plus x. That should be a plus, and that should be a plus right there. So this is actually a positive pi. So I'm actually getting a positive 3 pi halves right there. Cool. Okay. Fix that guy right there. So Austin's asking, why can't I pull out that 1/4? Remember that this 1/4 that's sitting right here is only multiplying just the sine of 4x. It's not multiplying the entire x expression of sine of 4x plus x. This 1/4 is only associated with the sine term right here. And the sine term went to 0 with both of my bounds, so it didn't end up affecting the component that I had on the inside right there, right? That 1/4 is not multiplying x. That 1/4 was associated just with these terms right there, right? And that was, yeah, an easy small mistake for me to make right there. So I dodged that one. So that's good. Um, cool. Okay. So I've got a 3 pi halves contribution there. And oh, that's okay. Sorry. I'm glancing over at my notes and seeing a 3 pi 16ths and getting all nervous, but I'm realizing in my notes I had multiplied the 1/8 through on all these, so we will get a 3 pi 16ths as the ultimate contribution from that one. I just got all nervous right there, but we're good. All right, so our last one here. This one looks like a bigger issue for us to fix right now. Now, the even powers have been nice to us because with even powers, we can do things like use the, like we just don't have identities that are associated with things like cosine cubed, right? Cosine squared, like squared trig terms are always good for some swaps, right? This odd one seems a little bit more troublesome to me. But kind of the lesson that I learned over here a moment ago is when I had odd powers previously, the contribution overall was 0 thanks to some nice bounds of integration. Let's go see if we're going to see that same type of action here. So let's pop over to Desmos again and check out cosine cubed of 2x. And so I just want to change this now to cosine cubed. Again, this is still, uh, oh, Desmos doesn't like doing any powers other than squaring, and -1 actually is powers. So you've got to actually write this thing as like cosine of 2x and then cube it. And so what I'm seeing here is it looks like we're going to get the same thing that we saw for cosine of 1x, right? It looks like this has that symmetry over symmetry over pi halves to where this bottom whole lobe is exactly the negative of the sum of the two upper half lobes. So I'm seeing here just visually, just looking visually in Desmos, it appears that the integral from 0 to pi should be 0 by visual inspection, right? I can see that we've got that symmetry over pi halves that's going to cause this integral to go to 0, kind of only because we had nice bounds, right? If this went from like 0 to, 3 pi fourths, then we don't have, then we lose our symmetry and we actually got to do some effort for this. So on the one hand, what I'm saying is because this is a definite integral, I can see graphically that the result is simply 0. And so that's all I'm going to say. On the other hand, it's also sort of like, but can we figure out what the integral of cosine cubed is? Like, what if this was an indefinite integral? Then we'd have to be able to do this here. So because this is definite, we just get to say it's 0, but that doesn't mean that this is like something that we're never going to have to consider. Like, I still kind of care. What's the integral of cosine of 2x cubed? For other more general purposes, right? So we get an easy fix in this case because it's a nice definite integral with nice bounds. But on the other hand, we're sort of skipping the integration process here. So I think I can at least say, for the purpose of this relatively large problem right here, we can kind of just say here, I'm just going to go, apparently I'm not going to write on this thing. Am I allowed to write yet? There we go. No, okay. Doesn't make any sense. I should be allowed to write. Oh, and now we're undoing things apparently. What just happened there? Bring that back. All right, pen. So this doesn't make any sense. Apparently on my eraser. Really? Was I? Okay, so So my comment here is just saying I can graphically see that this definite integral is going to be 0. So I'm good to go on its contribution to this overall value right here. But I still kind of want to know how to do cosine cubed. That's still like a thing of interest for us to be able to do here. So I'm going to go ahead and give it its contribution of 0 to the overall process here. This is now the thing that we're going to take 1/8 of. It looks like we're done with this guy now. A bit of a bear here on this one. We broke this thing up into lots and lots of parts, but we're able to do this guy at least. So 1/8 of, and what do we got here? 3 pi halves plus pi is 5 pi halves. And so I'm getting, for my overall answer here, 5 pi 16ths. So we've got our answer to our original question. What was the integral from 0 to pi of cosine to the 6th of x? Again, a lot of this centered on our recognition of whether the power on the trig term was even or odd. That kind of guided a lot of our decisions. Remember that trig functions have lots of nice symmetries. So this is very much a week of this course where you're really going to want to stop and say, hey, wait a minute, is that definite integral equal to 0? That kind of happens a lot with trig integrals and the typical bounds that are associated with them. So that's always something that you should stop and consider. It's going to save you maybe a lot of work. But again, we should kind of say to ourselves, well, in a sense, though, it's sort of just, it's not cheating. Like, you should definitely do that. You should definitely say things to me like, yeah, I looked at a graph. I could tell that based on the symmetry, I was going to get 0 from that integral. Totally fine thing to say. But in general, like, if there weren't bounds on this, we'd have to actually do the integration. So I still care to be able to do this integral right here. So let's go ahead and see if we can work our way through what our cosine cubed would have been. So this is I'm just breaking this out as its own example right here, doing the cosine cubed integral here. Let's go ahead and figure out an expression for how we can deal with cosine cubed. What we saw up here was when we had even powers, that allowed us to use identities to rewrite an even power of cosine as a cosine to the first, meaning that we actually directly have an antiderivative. When I have odd powers, I kind of lose that ability right here. And so what this leads me to believe is, I'm going to scroll back up even further now. It leads me to believe that it might be helpful for me to kind of mimic what we did in this guy right here, right? Now I'm seeing some things that are different, like I don't have an extra sine term to encourage me to make the u substitution of sine, but I still do feel like kind of isolating a single power to make the remaining powers even is usually in my best interest for all of the trig identities that we have that involve even powers of sine and cosine. We kind of like forcing ourselves to kind of have access to those right here. So let's go ahead and do that here. I think that it's going to be nice to rewrite this as like a cosine squared of x times cosine of x dx. And again, what I'm not seeing here is any obvious action that I want to perform, because what I don't see is a part and its derivative. But I'm thinking to myself, I'm like, is there any way that I know that cosine has a derivative that's sine, it's negative sine. I don't care about the negative. I can always deal with constant multiples when I'm doing integration. Is there any way to get some sine into this stuff? Well, yeah, we can just do the same move we saw before, right? If I rewrite my cosine cubed to look like this, then it feels to me like I do have the things that I want to see. If I make u be sine of x, then du is going to be cosine x dx, and I've got all this stuff into a polynomial integral again right here. So now I'm going to go ahead and say, let's let u be sine. Du can be cosine of x dx, and I've got a nice easy substitution to do here. Right, cosine x dx, that's just du. 1 minus sine squared is 1 minus u squared. Cool. Actually kind of easy once you see it, right? So we're going to get a u minus 1/3 u cubed plus c. And we just got to plot back in our sine. Sine of x minus 1/3 sine cubed of x plus c. So it looks like this cosine cubed one was something we could have done. Also notice real quick, remember up above we had the definite integral from 0 to pi of this expression. Technically it was of the 2x in there, so there would have been some extra constant multiples that are popping out right there. But we're getting 0, right? Notice that if we evaluated this guy both at 0 and at pi, then we're getting 0 for all the signs of 0. We're getting 0 for all the signs of pi. Technically up there, that would have been sines of 2 pi. I don't care. Sine of 2 pi, also 0. Like you can see this integrand, this result from this integral going to 0 if we evaluate it from 0 to pi, or 0 to 2 pi to kind of match up with the doubling that we saw up above inside of that argument up there. So this does agree with that 0 result that we got for the definite integral up above, but we can now see this from the definite integral version here as well. Cool. So let's kind of state some things that we saw here. General rules for integrating powers of products of sine and cosine. So one thing I want to encourage you to do is go look on page 484 of your textbook. In there, they have a little like red blocked out section that's going to list some rules. They list the rules differently than I list the rules. I kind of rephrase them alternative ways here. They have 3 cases, and I'm listing this only as 2 cases. I'm going to suggest that the primary case that we've kind of seen right here is if you have any number of odd powers. Look what we did every time we saw an odd power. Odd power on cosine, we picked off one of them. We rewrote the remaining even terms in terms of the other trig function, and we did a u substitution. Before, when we had an odd power, we picked off one of them to leave a single as well as an even count of them, 2, and then we did a u substitution, right? That seems to continue to be the trend right there. So case 1, if at least one of the powers is odd, you should pick off one copy of at least one of the odd powered functions. Maybe you have 2, maybe if they're both, cosine cubed sine to the 7th, you kind of pick one right there. Pick off one copy so that you create an even powered version of one of the 2 trig functions. Re-express the remaining even powers using the other trig function using the Pythagorean identity, and then go ahead and perform u substitution with the one that you didn't mess with, right? When I say the one you didn't mess with up here, we left the sine to the 6th alone, right? We picked off one of the powers of cosine cubed, we left the sine to the 6th alone, and then we performed our u sub on the sine to the 6th. That was our u that we used right there. And this is a good general strategy whenever we have one of our 2 trig functions having an odd power. The only thing that's kind of weird then is if we do have both of our powers being even, the problem with that is we don't have any partners to do, if we do the Pythagorean identity, we don't have like a function and its derivative in there anymore. So in those cases, what we're going to want to do is use our half angle identities, or our double angle identities, I should say. And possibly sines double angle identity as well as a kind of key one that's right there. So let me just real quick flip over and show you what I mean. When we're back here looking at our trig book insert here, what we can see is these half and double angle formulas are going to help us deal with all these even powers, right? Everything I'm seeing out here, cosine squared, cosine squared, and sine squared. This is also a good one right here. Notice that in this case, if we have two odd powers right here, if you have odd powers of sine and cosine multiplied together, maybe you want to rewrite the sine times cosine as 1/2 of sine 2 theta, right? If you divide both sides by 2 right there, that's potentially a useful one. And recognize that these half angle formulas, really, if you just square both sides of this expression and rewrite theta as theta over 2, like kind of double your angles in each of these guys, multiply theta over 2 by 2, multiply theta by 2 to get 2 theta. These are equivalent to our double angle formulas that are over here. So in general, those are good to use if we end up with either both powers being even or both powers being the same associated with that sine double angle identity that's right there. All right. But again, our broad strategy here is recognize that even powers of trig functions are kind of special. There's lots of identities associated with them that allow us to rewrite these integrands in terms of things that are going to be more useful for something like a u substitution. So, in some kind, I'm doing my bad thing again. I'm forgetting to click over right here. So whatever. I'm kind of just repeating myself right here about the idea of odd powers are kind of not great for us. So by picking off one odd power, it leaves us with even powers, which we like because they're associated with lots of our trig identities. So, as I've discussed with some people in some office hours, I think a good move for me to do to kind of help us all out with our, like kind of watching our videos here is I'm going to ask you guys to do some problems right now. So if you're watching this video not live, like a vast majority of you are doing, now is a good time for you to pause the video and see if you can work this one out yourself. Notice in this case, we have both powers being odd. So it looks like we're in case one, at least one of the powers is odd. So you should go ahead right now, pause the video, attempt to perform this integral right here. I'm telling you what answer you're supposed to be getting right there. So go ahead and do it on your own and verify that you're getting that answer. Another important thing that you should do along the way is that I know that a majority of you guys are huge fans of going to Wolfram Alpha and just asking it for the answers. You should go do that right now, and you should recognize that Wolfram Alpha is going to give you a pretty crap solution to this one. Their technique for doing this is going to take way more work than the technique that we're setting up right here. It doesn't really follow intuitively, and it uses rules that I guess I've never really formally seen anywhere before. It's not like I don't think they're true, but like it's a really weird solution. Since I don't think that you guys would even understand that solution if you just blindly copied it down onto your homework, I want to really emphasize to you guys that if I see solutions that I don't think you understand, I'm just not going to give you any credit for them. So I want to say to you, really dicey for you guys to just trust that you can copy answers from Wolfram Alpha for this week. It's not a really good idea. As we all know about trig expressions, there's like a million ways to rewrite trig things. So there's lots and lots and lots of different ways to do these. Some of these are intuitive and procedural. Some of these are what a computer algorithm would generate by just finding any list of rules that would technically get us there. I don't want an answer. I want a good answer. I want the easy route. I want the route that is a natural progression of thought rather than just an arbitrary assignment of rules and substitutions. So I am going to point out to you guys, you really shouldn't trust Wolfram Alpha kind of at all this week. It's not like it's giving you wrong answers, but it's giving you bad solutions, right? Their answers are good, their solutions are bad for lots of trig integrals. So you should avoid that. And you should go look at Wolfram Alpha and kind of laugh when you see the expression that they're going to give. So go ahead right now, pause the video, give this guy a try. Here's the answer that you should be getting. And another thing I'd encourage you to do, since it's hard, apparently you can't check your answers against Wolfram this week because it's going to give you a bunch of wild answers that aren't ever going to look like the answers you're going to come up with. It's important that you also take a moment to take the derivative of this expression right here and confirm that you are in fact getting the integrand back over here. Check your answer by taking the derivative and see that you get the integrand back right here as well. So go ahead and pause the video, do that guy right now. I'm going to move on and look at some more examples that you can resume once you're finished here. So let's go ahead and look at one other technique that we should definitely be remembering from trig class out here that we kind of need to know for some more manipulations of expressions inside of an integrand here. So we're looking at the integral of 1 over cosine of x minus 1 dx. The reason why this one's not going to be as nice as the others is because we kind of really like products of sine and cosine functions. Usually this is like addition and subtraction that we've got going on right here. I know that I don't have any trig identities that tell me some swap that's associated with cosine minus 1. I don't, I like, there's no, I don't even have to look at my identity sheet. I know it well enough to know that there's not an identity that looks like this guy. As we keep saying, if that was like a cosine squared minus 1, then I think that I'd be in a little bit better shape for rewriting this, but it's not, right? So I feel like I'm in a little bit of a pickle here. Other things, I don't have any way to rip that fraction apart, can't separate out the denominator terms. I'm kind of feeling to myself that when we have 1 over expressions, I do like anticipate getting like natural log stuff, but I don't really have a way to undo the like the chain rule that would be associated with that right there. So I don't feel like that's going to be a reasonable thing for us to do either. So now I want to like ask you, what do you remember doing back in trig class to manage denominators that are not as friendly to you, like cosine of x minus 1? And the important thing that should be sort of jogging your memory right now is seeing what do we do when we have addition and subtractions that we don't necessarily want inside of our denominators in particular. And we also kind of want to remember as our other like leading hint of intuition here is saying, man, it would be really cool if down there at the denominator that was actually like a cosine squared of x minus 1. Then I would at least have some manipulations I can do. So what is the like algebraic technique that you remember that sort of helps us do a version of squaring things in a legal manner? Okay, good. You remembered. Let's remember that we can always deal with conjugates to help us, in a sense, square things in a legal fashion, right? So conjugates are when we do things like a minus b times a plus b and getting out a squared minus b squared. It's sort of saying start with some difference or sum, multiply by the same difference or sum, but swap the sign between them. And what you're going to get back is the original, the difference of the positive and the negative term right here, but each term individually being squared, right? So what I think I want to go ahead and do with this integrand right here is I'm going to go ahead and multiply by the conjugate, cosine of x minus 1, times, and I'm going to multiply by cosine of x plus 1 over cosine of x plus 1. Right? Hitting, oh my gosh, what's wrong with me in my parentheses all of a sudden? Right? So all I'm doing is multiplying by a fancy version of 1, so that's a legal multiplication for me to do inside the integrand. But what this is going to do is this is now going to give me a cosine squared minus 1 in the denominator, which is something that I sort of like, right? That's a nicer term for me to have when it comes to trig expressions down here. This is going to give me cosine squared of x minus 1. And the whole reason I like this is because I know that that sounds more to me like a trig substitution that I can do, right? I feel like this is where I want to go in the direction of cosine of x plus 1 over sine squared of x, right? By hitting this thing with the conjugate, I was able to convert, in a sense, cosine of x minus 1 into sine squared of x. And I think the reason that I like that is because now I'm starting to feel a little bit of that u sub flavor out here again, right? Now I got some sines, I got some cosines. I feel like this is some stuff that I can do. Part of my problem, though, is if I just straight up right now go ahead and say, all right, let's let u be sine of x. Well, I don't have for du cosine of x plus 1 dx, right? That plus 1 is now the thing that's kind of screwing me up right here. But that's okay. This minus 1 is a problem in the denominator because we can't rip apart denominators. A plus 1 up here in the numerator is not as big of a problem because I can just rip this up into two different fractions now. Right? So I'm going to go ahead and do that. I'm going to write this as the integral of cosine of x over sine squared of x dx plus integral of 1 over sine squared of x. Right? So I've ripped up that fraction cosine of x plus 1, the numerators, into their own two different fractions, own two different integrals right there. Now, it looks like this first guy, so I'm now dealing with just two totally separate integrals. This one, it has exactly the structure that we sort of want it to have for a nice u substitution. If I let u be sine, then du is going to be cosine of x dx, and I've got exactly those parts right there. So let's go ahead and do a nice u sub for this guy right here. That's going to lead me to a, let's see, an integral of just a 1 over u squared du, right? U is sine, so I get a u squared in the denominator. Cosine x dx is the numerator, and that's exactly what I'm swapping out for, du right there. So that's a pretty good one. I can do that integral. What's going on over here? Well, I know that 1 over sine squared is, shouldn't put a plus sign between a substitution and expression. I know that this is really the same thing as the integral of, what is it, 1 over sine is cosecant squared of x. And don't forget that you know some antiderivatives. I'm going to do a bunch of scrolling right now. Ah, cosecant squared. It looks like that's just the antiderivative of cotangent. We've got the negative here, so it looks like the integral of positive cosecant squared should be negative cotangent. We just straight up know this integral. This is just a direct antiderivative. Not doing any substitutions, not doing any trig tricks here. If the derivative of cotangent is cosecant squared, then the integral of cosecant squared is cotangent. And I just dropped my negatives when I verbalized that right there. But that's because the negative is easy to handle with integrals and derivatives, right? Just shuffle it around to where it belongs, right? In this case, I'll stick it on the cotangent. So it looks like this guy right here is just a direct integral. There's no tricks to this one right here. We're just getting for this guy minus cotangent of x. I'll put my plus c on right now. Now all I got to do is this relatively easy antiderivative right here. That's really u to the negative 2. I'm going to add 1 to the power to get u to the negative 1. But if I were to take the derivative, a negative would pop down, which we don't have here. So I'll introduce the negative to counteract the chain rule here. And all I got to do is undo my substitution that's right here. And it looks like I'm getting negative 1 over u was sine. And so for my final answer, I think I'll rewrite this guy as negative cosecant of x minus cotangent of x plus c. Right. So honestly, I kind of laugh that in this week, I feel like some of the trickiest integrals to do for most students are the ones where there's no trick at all. So don't forget that this is just a direct antiderivative. Right? That's just direct antiderivative for that guy right there to get that negative cotangent, right? No tricks at all. Took the derivative, undid the derivative right there. Just picked up a negative is the only exciting thing that happened there, right? So again, don't forget about your conjugates. Anytime you see sine or cosine plus or minus 1 and you are sitting there just wishing to yourself that the cosine was squared, you can make it so with your algebra beat and stick right here. And again, this is like I've kind of joked in the past. I let my anger motivate my math here. This is me looking at this and being like, I don't know what I'm supposed to do with this dang thing. Why can't this stupid cosine just be squared so I can deal with it? I allow my anger to motivate the math that I'm doing right here, saying, fine, I'm going to make that cosine squared, and I can do that with a conjugate right there. I think it's like sort of this like silly thing to say, but like I do think there's value in saying like, if you were allowed to modify the problem to make it easier for yourself, what modification would you do? Then think to yourself, was there any way I can actually cause that modification to happen so that I do have that easier integrand? And we do. The conjugate's sitting right there. So like wishful thinking is not a waste of your time necessarily. Wish what you wish the integral would be, and then think, is there some algebra I can do to make it that way? So don't forget about your conjugate. It's a good thing to do here, particularly when you have addition or subtraction of individual powers of sine or cosine. This is a good way that we can make them be squared, and we really like those squared trig terms out there. All right, all right. So far we've just spent like over an hour here talking only about sine and cosine basically. So let's see if there's some other that we can do. and I'm saying can do in a very awkward way right there because you can't do this one. This one's hard right here. Let's go ahead and do our secant of x integral. This one is straight up a trick. This is one of these ones where there's no way that any of you would ever come up with this on your own. There is no way that I would ever come up with this on my own. This is a straight up trick. This is one of those ones where I'm going to do this just to show you that sometimes these are, in a sense, beyond our brain's grasp right here. So if it ever comes up that you need an integral of sine in the future, you're going to be able to simply just state, and from the book, and from our notes, and from lecture, we know that the integral of sine is blank. And I'm not going to ever expect you to ever directly do this integral right here. This is a straight up trick to do this one. Technically, there are a couple different ways that this one can go down. All of them are straight up tricks, and I'm just going to do the easiest trick that there is that's associated with this one right here. So this is one where I'm showing you like, bummer. Some of these are just hard to do right here. So here's the dumb trick that we're going to do with this one. In a similar sense to how we did our conjugate before, where we multiplied by a fancy fraction that was equal to 1, but that helped us get the terms that we wanted, we're also going to multiply this guy by a fraction that's equal to 1, and it is going to give us the terms that we want, but there's no way that you would have ever guessed this one, because it's definitely not even anything like a conjugate or anything like that. So here's the kind of ridiculous trick that we're going to do for this one right here. That's sort of beyond us. Oh, did I say sine right there? Yes. The secant one right here is what we're doing right there. Integral of secant is something that I would never expect you to come up with on your own. And if it comes up in any like homework problem, you are allowed to simply say, I know that the integral of secant is this thing, and just say it because this is a silly one right here. So here's the silly fraction that we're going to multiply this by, and let's see what happens. Secant plus tangent is what we're going to multiply by. And I want to show you the light bit of intuition that suggests that this is not like a blind guess as to what we would want to do right here, right? So that's my fancy one that I'm going to multiply by. I'm going to scroll up to our derivatives and show you at least some intuition as to why I think this is a reasonable thing to do, barely, right? What's going to happen here is the secant is going to multiply through the numerator, and it's going to give us secant squared plus secant tangent. I'm going to scroll up to the top now. Secant squared plus secant tangent. Notice that secant squared is a direct derivative, and secant tangent is a direct derivative. And what are they the derivatives of? Secant and tangent. So this has a bonus factor. Notice, like in a sense, like factor out secant from this and factor out secant from this. It's literally giving you secant and tangent as the derivatives of secant and tangent. This is going to nicely set us up for a U sub. That's, again, not one that you would have seen, but this actually works out really cleanly once we go to do it right there. It's just, I wouldn't have ever guessed this, right? So now when I go ahead and expand, when I multiply this out, we're going to get the integral of secant squared of x plus secant tangent, all divided by secant x plus tangent x. And so it looks like now the derivative of secant plus tangent, the derivative of secant is secant tangent, the derivative of tangent is secant squared. The numerator is the derivative of the denominator in this new fraction that we've built right here, which is almost unbelievable. So now I'll go ahead and do a u equals secant x plus tangent x, and we will find then that du, the derivative of secant is secant tangent, plus the derivative of tangent is secant squared, all that dx. That's the whole freaking numerator right there. Ridiculous. So hopefully you are laughing about this one. And again, this is like not something I'd ever expect you to do or come up with on your own. I'm just showing you sometimes these have ridiculous tricks to make them happen right here. But this all boils down now to literally, like this whole numerator is just the du part. The whole denominator is just u. This is just straight up 1 over u du now, which is just going to be the natural log of u, which is just going to give us the natural log of secant x plus tangent x. And so again, with this guy right here, you are certainly welcome to just say, I know that the integral of secant x is the natural log of secant plus tangent. And you can simply use that as a result if it ever comes up anywhere, because that's a bit beyond our grasp to just come up with algebraic manipulations like this. And honestly, even if you did this, which nobody in their right mind would ever just straight up guess this, then you got to see that that's actually a full whole u sub for this whole entire expression. Really simplifies it right here. So kind of ridiculous, but kind of cool to see, I guess, in a way here. So I kind of was saying like, oh, we've only looked at sines and cosines. Let's see others. It's not like everything that's not sine and cosine is just impossible. This kind of one, and this isn't impossible. It's just weird. This one right here is a little bit weirder than the rest. So let's look at some that we maybe actually can do right here. So let's go ahead and take a look at an integral of secant cubed now. And we'll see that it's got some relation to what we've been doing with the sines and cosines, but also a little bit of a relation back to our secant integral that we just did right there. So let's take a look at this guy here. So secant cubed, well, what my intuition is telling me from what we've been doing for the last hour plus right here is I don't like odd powers. That's kind of been like the broad lesson that I've learned here. Odd powers on trig functions, not really what I want. So I'm going to do my first piece of intuition from the last hour tells me I kind of feel like I want to write this as secant squared x times secant x dx. Right? Now, the whole reason that we've liked picking off one individual term of this and leaving a squared term is because that leads us to a Pythagorean identity statement. And so my question is, and again, I'm just trying stuff right now. I'm just saying, I don't know. I'm like going to guess that there's some relation between our sine and cosine strategies and our tangent and our secant strategies and stuff like that and our cosecant strategies. So let's see if that's going to feel out in the right direction right here. I'm asking myself, how do you rewrite secant squared? I'm assuming that all of you, like me, typically forget your non-standard Pythagorean identities. I remember sine squared plus cosine squared equals 1 all the time. I kind of usually forget the secant ones. So popping over real quick, secant squared. It looks like secant squared is the same thing as tangent squared plus 1. Let's see if that's helpful to us, because I know that there is no secant squared anywhere else on this page, so I'm pretty hopeful that that's actually going to be useful to me. Otherwise, I got to rewrite secant squared as like 1 over cosine squared and see if I can do some manipulations over here, but that I'm kind of hoping that's not the case. So tangent squared plus 1 is secant squared. Let's go ahead and see if that's going to be useful to us. One of the 3 Pythagorean identities is secant squared equals 1 plus tangent squared. All right. So if I were to do that here, I'm going to get a 1 plus tangent squared times secant dx. So what's good, what's bad about this? Well, one of the good things that I'm seeing here is that I do almost kind of have some sort of u sub to set up here, right? In the sense that maybe like the derivative of tangent is secant squared. I kind of have the wrong powers on those things right there. I don't know. Is this going to be a direction we can actually make this thing happen? Um, you know, So I feel like I'm sort of dancing around it right now, right? I've got tangents, I've got secants, one of them squared, but like the wrong one squared for the relationship that we actually have right here. So it doesn't seem like that's going to work out here. Um, so now I'm thinking to myself other things like I still sort of feel like that relationship's going to be in there, but I don't quite see how. So now I'm thinking to myself like, is there some like integration by parts maybe that we want to set up for this guy here? Um, like maybe like I don't know, like do I even really want this guy right here? um it's unclear, right? Kind of like recognize again that this is just like a, I don't know, I'm just trying stuff right here. I do feel like there's going to be this relationship where we want to think about both the fact that secant squared can be rewritten as 1 plus tangent squared, and the fact that the derivative of tangent is secant squared. It seems like there's going to be somehow some tangent thing getting involved here. But again, I have sort of the wrong powers set up right here, right? So here's the thing I'm thinking. Maybe we can set up some integration by parts to help make this guy happen, right? So if I'm looking back here at my secant squared of x times secant x dx, maybe we can set up some IVP here, right? Some u and some dv. Now, what parts should we pick with what parts, right? Like, did I write that in the order that we kind of want that to be? Should I be picking u to be secant squared, or should I be picking u to be secant? And again, I'm just trying some stuff right here. But here's the thing that I know. Whatever I pick for u, I will have to take the derivative of. Whatever I pick for dv, I'm going to integrate. And so I'm asking myself, what's the thing that seems like it's going to have like a sort of a cleaner integrand right here? Well, I actually know how to integrate. I know how to integrate secant squared. It gives me tangent because that's the derivative, right? Derivative of tangent secant squared. So I'm kind of guessing to myself that this might be the nice place to pick secant of x dx, because that would lead me to just have a v that's just tan x, right? That's a pretty clean v term that's going to be nice. If that's the case, then that's going to leave me with u being secant of x and with du being secant tangent. Again, unclear if we're heading in the right direction, but we're trying some stuff. I feel like there's got to be that tangent involvement somehow with some of this stuff in here, right? So let's see. If I do this now, what am I getting? It looks like we're going to be getting, that's not what I write for integration by parts. Now we should be getting uv minus integral v du. So this is going to be giving me uv, which is secant tangent, interestingly enough, secant tangent, just like, oh, I should put my dx right there, just like we have for the du term, by the way. So I'm going to get a secant tangent, that's uv minus integral of v du. Du was secant tangent times an additional tangent gave us a tangent squared on the inside. Did this help us at all? So I've replaced my integral I can't do with a different integral. And now I'm asking myself, is this actually the helpful thing that I actually want to do right here? Well, it seems like, again, we're in this situation where we don't really have the powers that I was kind of hoping to see for myself right here. Um, right? We still have the same wrong power integral, where I really wish this was a tangent and a secant squared. In that case, that would be like a really, really easy u sub for us, right? We have kind of have that same issue as this right there, where they're sort of flipped as to what I want them to be. But there's one tiny difference between this guy and the one that we saw before, which is that I can again think about my Pythagorean identity here to do a little bit of rewriting with this guy, right? And what that would do, notice, if I use the Pythagorean identity now that I've done my integration by parts, look at what it's going to do. My Pythagorean identity would swap out tangent squared with a secant squared minus 1, and secant times secant squared minus 1 is going to give us more secant cubes. Oh my gosh, I've come full circle. That means I can't do this, right? Well, if you've done your homework from week 4, then you should actually know that recreating new integrals that are the exact same as your original integral is actually very good news for us, right? This is what we refer to as that dump truck integration, where you got on the written homework for week 4, number 3 is a very, very similar process as to what we're seeing right here, where we're sort of doing a cyclic setup for our integrals. So doing integration by parts and generating the exact integral that we started with is actually helpful. And the thing I'm going to do here that it makes it not obvious that it's helpful is to remember that on the left-hand side of this integral, or this equal sign, is the integral of secant cube. That's what we're trying to identify what it is, right? Um, But if we use the Pythagorean identity, we get more integrals secant cubed, which is actually good. Right? So in the week 4 homework number 3, you did exactly this type of strategy here. So the two important things I'm going to do are this. I'm going to swap out tangent squared 4, and I can see my identity up here. Tangent squared is secant squared minus 1. I'm going to write on the left-hand side, I'm not just going to write equals, 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 equals. I'm going to remember what is on that left-hand side over there. Right? So I feel like I wrote that paragraph right there a little too close. So we're getting here integral of secant cubed of x dx equals secant x tangent x minus integral of secant x times, and I keep on forgetting what order it goes. That's okay. You can always look these things up a million times like I do. Tangent squared is secant squared minus 1. So, doing a little bit of shuffling around here, I'm getting this is the integral of secant cubed of x minus secant x dx. I'm going to rip that apart. Oop, I made a terrible typo over here. That's not a squared, that's a cubed. That matters. So I distributed this negative and ripped this up into two separate integrals because it's just an addition or a subtraction. And you should notice there's two nice things that happened here. One, we already know the integral of secant of x. I'm just going to go ahead and copy it down from our previous work right here. We already did that one. There's a reason I made this example 6 come right before example 7. So we're going to use the integral of secant. The other thing I'm seeing is that this integral of secant cubed that we've introduced is literally exactly what we're trying to deal with over here. So there's two things I'm going to do on this next line. One, I'm going to add this integral of secant cubed over to the left to get two copies of it. Two, I'm going to rewrite my integral of secant cubed as exactly the result that we got in the previous example, and we're actually done. This is a very sneaky roundabout way to come at this solution here, right? So we're getting two copies of secant cubed of x dx equals secant x tangent x. This term got added to the other side. That's where the 2 came from. This term, secant x, and what was our result from this? I'm going to scroll up and find it. Integral of secant of x. Wait, did I just go past it? Integral of secant of x. We got natural log of secant plus tangent. We're done. That was sneaky. That was sneaky. It was not clear at all to me that this was going to end up being, and again, I don't think I used that word last week because I didn't personally do the example that was associated with it. But that dump truck integration, and by the way, I'll get the plus C on that guy right there. Dump truck integration is this process of attempting to find some integral, doing some integration by parts that generates another copy of that same integral. That seems unhelpful because now you just have to deal with it twice, but this is actually good because we can just move this over to the other side, recognize that we have multiple copies of it, divide by the coefficient, and we are good to go. So 1/2 secant x tangent x plus 1/2 natural log. Oh wait, sorry, that was secant x times tangent x. This is secant x plus tangent x. C, technically that C got divided by 2, but I don't care. That's a basket for your constants right there. Once we go to solve for it, we would get the right things either way. So there we go. That one was not obvious right there. We did some wonky things. We tried some stuff. It was like I tried to make my U subs. They just didn't quite feel out. I guessed some things for integration by parts. I guessed the parts that I thought were going to be most useful to me. I guessed DV to be secant squared because I knew I could integrate it to get something easy right there. And all of these guesses that I made right here, I just said, I don't know, what else would I do? I'm going to guess the easiest possible thing, and it ended up kind of working out right there. Yeah, did I get all those? I think it's all just pluses right there, right? That minus got added over to get the 2 copies right there. Yeah. Cool. So that was a tough one right there. Secant cubed, not easy. And also notice that even if you could see this whole process for secant cubed, you still would have had to have known what to do with this integral of secant right here. Honestly, the integral of secant, I would say, is harder for you guys to come up with than the secant cubed one is, aside from the fact that secant cubed involves the secant. So tough stuff right here for sure. But again, the point is these follow the same broad strategy of saying things like, I don't like odd powers of trig functions. I make things even powers of trig functions all the time so that I can do things like take advantage of Pythagorean identities and things like our double angle formulas for sines and cosines, stuff like that. I'm remembering that I want to think in terms of U sub because U sub is straight up easier than integration by parts. But when I saw my U sub just not working out with the powers that I actually had because I had the squared on the tangent instead of the squared on the secant, it said to me the only thing I would know to try is integration by parts. So again, I know that this feels like that's something like sort of unbelievable for you to do on your own, but like what else would you do? And so again, I love that like last week and this week, the major theme of this is persistence. If you just give up, then that's the only way you're not going to make it through here. My guess is, well, I guess I knew what I was going to do already with these. Like, what else would you have guessed to do? There's not really like, it's not like there's like 1,000 different U subs to try and 1,000 different integration by parts to try. Try the ones that seem the easiest and most doable to you always. If it seems gross, try something that's easier first. Try the grosser ones later. Maybe it has to be the gross one. I would never guess that first, right? I guessed the nicest things like making dv secant squared so that v was tangent. That was easy. Versus making dv tangent or being secant and then having to get the integral of secant for v, that wouldn't have been nice at all. We would have had this for our v expression right there. I don't think I would have been able to deal with that inside of my next integrand, so I didn't guess that, right? Like your first guess being the easiest thing did lead us in the right direction for all like 3 layers of guessing that I did right there, right? I'm saying again, I again don't know what to do with this, but if I do my Pythagorean identity, oh, what do you know? It generated some terms that we'd already seen, allowing us to resolve for that integral right there. So I consider this problem to be like at the very fringe of the stuff that I expect you guys to be able to do. This is like as hard as it would ever get for something that I'm going to directly ask you to do right here. Harder than this, we're just entering into the territory of the weird stuff associated with secant and these types of things right here. That's I hate calling anything in math a trick. This to me qualifies as a trick right there. So therefore not something I would ever expect to you guys. This is a sequence of guesses, but a bunch of the easiest guesses that you would guess in each context right here. So a very hard problem here, but also very doable. And it involves all of our intuition. It involves our integration by parts. It involved our identities. It involved trying U subs. It involved dump truck integration where we combine 2 different integrals to just say, now I know the value of that integral since I got more copies of it. A lot of good ideas that are involved in this one right here. So I really like this problem. So once again, I'm going to now ask you to stop the video if you're watching this after the fact and do another one for yourself right here. And you should attempt to do secant to the 6th. I've done secant to the 1st. I've done secant to the 3rd, which are both odd powers of secant. I am now asking you to do an even power of secant problem. And on this one, I'm going to give you 2 hints. Here's the answer that you should be getting. All right, there's your answer. And the 2 hints that I'm going to give you are, we like even powers because they allow us to write things like more even powers. So there's your first hint. And your second hint is that's going to be a substitution that you're going to want to make happen in there. Figure out where u equals tangent of x is a useful substitution. So these are your 2 hints for you to pause for a second and do this guy on your own. And again, I'm going to say to you, go and look at the answer in Wolfram after you've gotten your answer out and laugh out loud a little bit and confirm for yourself that copying solutions from Wolfram Alpha is a really, really bad idea, especially associated with this week's content right here. Trusting a computer algorithm to come up with your good thoughts for yourself is a bad idea. So again, you should also take your derivative of this guy right there to confirm for yourself that the derivative of this expression is in fact exactly secant to the sixth. And honestly, that's no trivial thing to do yourself right there. That is going to involve you doing some trig identities and stuff like that, that you kind of need to see the factoring and the identities on your end as well right there. So even the confirmation of this one with the derivative is not trivially easy right there. All right. So last thing I want to throw at you, and we'll call it a day right here. I'm not going to do an example, but one thing I want to point out to you is that so far everything that we've looked at has maintained the exact same argument inside of the trig functions as any other thing in the expression. These were all like cosine of x, or sine of x, or tangent of x, or secant of x. Well, what happens if we not only have a product of two trig functions, but the arguments inside aren't the same? Now, if I were to do anything with these guys, like if this was a cosine squared and a sine to the sixth, none of my u sub stuff is going to work out here because of the fact that I can't swap out sine being sine to the sine of 5x for like a cosine of 2x. If the arguments inside of your trig functions are different, then sort of none of our strategies work here today. Fortunately, there are some relatively easy trig substitutions you can do. So again, I'm not going to do this one. This is the last example in section 7.2 in our textbook. And all they're going to do, and I'm going to show you on the trig identity sheet where the identities are that you can go with this guy right here. What we want to do is use the product to sum formulas right here. So the product to sum formulas, I'm going to pop over and look at them, and that'll be it for us today here. The product to sum formulas over here are going to show you ways that you can rewrite. Oh, why can't I scroll here? Come on, just give me the thing. That you can rewrite things that are products like we have right here, like a sine and a cosine. You need to do a little bit of math to figure out what alphas and betas you can use to describe the 2x and the 5x that we have. In which case, you'll be able to rewrite your product of two things with different arguments as a sum or difference of two things. And while they have different arguments, it no longer matters because now you can just straight up do the integral of sine of alpha and straight up do the integral of sine of beta, or whichever of the four it ends up being right here. So this sum the product formula is a good way to handle a situation where you have a product of two trig functions that have different arguments. You can instead use your sum to product formulas to rewrite the product as a sum. And then it no longer matters that the arguments are different from one another because you can just do it as two completely separated integrals as opposed to the integral of one product. You get two integrals of standalone trig functions, and then you're just doing a direct integration with kind of no problem right there. Then you're just doing things like the integral of sine of 4x, and it's going to be negative 1/4 cosine of 4x, and you're done. Real easy. A direct integral, technically a light u sub in there to deal with our constant multiple if you're still writing out that u sub. But our sum to product formulas are a good thing to do, or product to sum, I should say, anytime we have those differing arguments inside of our trig functions that are right there. So I think that one, and again, I think that one's one of our like easiest ones to do. I really don't expect anybody remembers these identities right there, those formulas. Those are the ones that we use like the least in trig class, but they come up to be useful in this case right here. So again, don't remember them, look them up in your sheet. Remember that I have posted this sheet for you in Canvas, since I don't think that all you guys have your textbook anymore. So go and grab this PDF from Canvas right here. It's literally exactly the one that I've got open right here. You should be using this pretty heavily as your reference for this week and all trig integrals that you always do out there. So grab that guy, and that's going to be one of your keys this week. And also, I'm just remembering as my last thoughts here, like I got Desmos up right now. Keep remembering also, a whole bunch of definite integrals in trig are going to be equal to 0, and you should be able to graphically identify when that's going to happen, even if they're not over bounds that are negative a to positive a, like we saw with our original symmetry arguments in the textbook. So still use Desmos to help you see when you get some easy zeros for some of your definite integral values here. So use your trig identity sheet. Use Desmos for definite integrals. Don't use Wolfram Alpha this week. It's not your friend this week. It's going to show you hard, stupid ways to do things that are not what I care to see. So do things the smart way. Use the strategies that we've got. Again, the book also lists some more techniques associated with our tangent stuff and our secant stuff, just like our book lists the general strategies for our techniques for sine and cosine. So make sure you take a look at those. But again, there's a lot of intuition behind these things. This is definitely a practice-based thing. A lot of these things that we did here today, particularly our last example, are pretty tough. So these do take a little bit of practice. That's why we get all the good MyOpenMath stuff that's out there. So be persistent with these. But as always, hit me up with questions about homework. Don't just sit and bang your head against the wall for 4 hours on a stupid integral. Hit me up so I can give you some pokes in the right direction for some of these. Because I might be able to save you a lot of time and still allow you to do most of the thinking on some of these things, which is the way all this should be. So that was a long enough video here for today. I'm going to go ahead and wrap it up. Tomorrow, we're doing more trig, but the point is tomorrow, none of the integrals are going to come with trig expressions already in them. We're going to put the trig in it ourselves to use more of our trig identities to take advantage of some of these things. So I will see you guys in our next video for trig substitutions. Have a good one, everybody.